Okay, this video continues with section 11.5. This theorem is the distance between a point and a plane. Suppose we have a point in space Q that's not on the plane, and we have a plane given here. We want to determine the distance between the point and the plane. Now, one way to determine that distance, look at this dotted pink vertical line, would indicate the distance between the point Q and the plane shaded in gray. To find that distance, you can project the PQ vector, where P is any point in the plane. We're going to project the P, which is at any point in the plane, to the Q given point, or project a PQ vector onto the normal vector, and this is a vector that's normal to the plane. The length of that projection of the PQ vector onto the n vector is the distance from the point to the plane. This can further be simplified by taking the dot product of PQ, again P is any point in the plane and Q is the point not on the plane, with the normal vector, and you can find the components of the normal vector if you're given the equation of a plane. The dot product goes in the numerator, divided by the length of this normal vector. And of course, distance can only be positive. That's why we have our absolute value in the numerator. In this example, we want to find the distance between the point, which is point Q, 1, 5, negative 4, and the plane given by 3x minus y plus 2z equals 6. We need to find a point on the plane, we'll call it P, and we want to find the vector from P to Q. Project that PQ vector onto the normal vector and find the magnitude of that. Okay, so you can identify the normal vector by looking at the coefficients of the x, y, and z. The normal vector is 3, negative 1, 2. Now you find any point on the plane. It doesn't matter which one. So to make it easy on yourself, you can let y equals 0 and z equals 0 and solve the equation to find a point P, 2, 0, 0, which is the x-intercept. So now we want to take this point P and find a vector from P to point Q. And that vector would have components, again taking the terminal point, subtracting the initial point. The components of vector PQ are negative 1, 5, and negative 4. Now we want to find the dot product of the normal vector with the PQ vector. Take the absolute value of that and then divide it by the magnitude of the normal vector. Okay, the dot product is found by multiplying the corresponding components and adding the results together, and then we know how to find the magnitude. And we find that the distance from the given point Q and the plane is 16 divided by the square root of 14. Now for this example, I'd like you to try this one on your own. It's pretty much the same question as the previous example, just slightly different numbers. So we are given a point that's not on the plane. We're going to call this point Q. And the normal vector we're going to find using the using the coefficients of the equation of the plane. Now we do need to find a point P. P can be any point on the plane. I'm going to find P by setting y equal to 0 and z equal to 0. And the equation of the plane, if you let y and z both equal 0, you get x equals 4. So that's going to correspond to the point 4, 0, 0. Now we want to find the vector from P, which is on the plane, to Q, which is not on the plane. The components of those vectors, of that vector, and taking the terminal point minus the initial point, 3 minus 4 is negative 1, 2 minus 0 is 2, and 1 minus 0 is 1. That's our PQ vector. Now our normal vector is found by taking the coefficients of the equation of the plane, the coefficient of the x is 1, the y is -1, and the z is +2. Now we can apply this formula to find the distance. The distance is equal to the absolute value of the dot product. So we're going to multiply those corresponding components. -1 times 1 is -1. 2 times -1 is -2. And 1 times 2 is +2. Absolute value of that in the numerator divided by the magnitude of the n vector, which is 1 squared plus 1 squared plus 2 squared, which can be simplified to the square root of 6. The numerator, when you simplify this, -3 plus 2 is -1. The absolute value of that is 1 divided by the square root of 6. So the distance from point Q to the plane given is 1 divided by the square root of 6. This theorem shows how to find the distance between a point and a line in space. To find the distance between a point Q, which is not on a line, and another line in space is given by the following. The magnitude of the cross product of the PQ vector with the U vector divided by the magnitude of the U vector. Now U is a direction vector for the line. That would be a vector that's parallel to the line, and P is a point on the line.